Hello, my dear students. In the last class, we have already discussed about inductive effect and electromeric effect. These are electron displacement effects in organic reactions. Today, we will discuss about mesomeric effect, hyperconjugation, and steric effect. These are also electron displacement effects in organic reactions. The term electron displacement effects refers to the effects involving bonding electron displacement. It may be partial or complete. Either takes place inherently in a molecule, that is permanent effect, or brought about under the influence of an attacking reagent. This is called temporary effect. Firstly, resonance effect or mesomeric effect. The presence of certain groups introduces resonance or mesomerism in certain molecule, thereby causing generation of centers of low or high electron density in such system through delocalization of pi or n electron. Such an electron displacement effect caused by the phenomenon of resonance or mesomerism in a molecule is called resonance effect or mesomeric effect. It is called R effect or M effect. In this example, a double bond exists between two carbon atoms and a carbonyl carbon also exists. Then the presence of carbonyl group introduces resonance in the molecule, then thereby create a positive charge and a negative charge, that is causing generation of centers of low or high electron density in the molecule through the delocalization of pi electrons. That is, the mesomeric effect is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and a lone pair of electrons present on an adjacent atom. There are two types of mesomeric effect, depending upon the nature of the group present adjacent to a multiple bond in a molecule. These are minus M or minus R effect and plus M or plus R effect. The negative mesomeric effect, that is minus M effect, is shown by substituents or groups that withdraw electrons by delocalization mechanism from rest of the molecule and are denoted by minus M or minus R. The electron density on rest of the molecular entity is decreased due to this effect. For example, NO2, carbonyl, cyanide group, carboxyl group, SO3H group, etc. The positive resonance or mesomeric effect shown by the group when they release electrons to the rest of the molecule by delocalization. These groups are denoted by plus M or plus R. Due to this effect, the electron density on rest of the molecular entity is increased. The example for such groups are hydroxyl group OR, SH, SR, NH2, NR2, etc. For example, the negative mesomeric effect is shown by cyanide group in acrylonitrile. The electron density on third carbon decreases due to delocalization of pi electrons towards cyanide group. The negative resonance effect is shown by nitrobenzene. Here, the transfer of electron is towards the atom or substituent group attached to the conjugated system. The other groups showing minus R effect are carboxyl, aldehyde group, carbonyl group, cyanide group, NO2, etc. The nitro group in nitrobenzene shows minus M effect due to delocalization of conjugated pi electrons. Here, the electron density on benzene ring is decreased particularly on ortho and para positions. This is the reason for why nitro group deactivate the benzene ring towards electrophilic substitution reaction. An example for positive resonance effect is shown by aniline. The NH2 group in aniline also exhibit plus R effect. It releases electrons towards benzene ring through delocalization. The NH2 group in aniline also exhibit plus R effect. It releases electrons towards benzene ring through delocalization. As a result, the electron density on benzene ring increases, particularly at ortho and para position. Thus, aniline activates the ring towards electrophilic substitution. It is also shown that the electron density on nitrogen in aniline decreases due to delocalization, which is the reason for its less basic strength when compared to ammonia and alkyl amines. Another example for showing positive mesomeric effect is phenol. In phenol, the OH group shows plus M effect due to delocalization of lone pair on oxygen atom towards the ring. Thus, the electron density on benzene ring is increased, particularly on ortho and para positions. In phenol, the OH group shows plus M effect due to delocalization of lone pair on oxygen atom towards the ring. Thus, the electron density on benzene ring is increased, particularly on ortho and para positions. Hence, the phenol is more reactive towards electrophilic substitution reactions. The substitution is favored more at ortho and para positions. Another electron displacement effect is hyperconjugation or Baker-Nathan effect or no bond resonance. The phenomenon of resonance generally involves delocalization of pi or n electrons through pi or pi n conjugation. Hyperconjugation may be regarded as the extension of resonance effect into sigma pi or sigma p conjugation. That is, delocalization of electrons by the overlap of a sigma bond orbital with a pi or p orbital is called hyperconjugation. Since delocalization of electrons brings about a lowering of energy, hyperconjugation is a stabilizing interaction. The conjugation of sigma bond orbital of any of the three carbon-hydrogen bonds of the methyl group with a pi orbital constitutes hyperconjugation in propane. In the case of propane, the methyl group is attached to a carbon-carbon double bond that has a pi bond. The conjugation of sigma bond orbital of any of the three carbon-hydrogen bonds of the CH3 with the pi orbital constitutes hyperconjugation. These are the resonating structures of propane by hyperconjugation. Since there is no bond between carbon and hydrogen atom in these structures, hyperconjugation is called no bond resonance. Propene is more stable than ethane as the former contains 3 alpha hydrogen atom and the sigma pi electron delocalization exists in propane and not in ethane. Ethane does not possess even alpha carbon atom. Then, 2-butane is more stable than 1-butane. Why? Hyperconjugation becomes more pronounced as the number of alpha hydrogen atom on the carbon atom near to the unsaturated carbon atom increases. In the case of 1-butane, there are only 2 alpha hydrogen atoms, but in the case of 2-butane, there are 6 alpha hydrogen atoms. So, in the case of 2-butane, there are 6 hyperconjugative resonance structures. But in the case of 1-butane, there are only 2 hyperconjugative resonance structures. So, 2-butane is more stable than 1-butane. The increasing order of stability of alkenes with increases in the number of methyl groups on the double bond. That is, increasing the number of alpha hydrogen atom on the carbon atom nearer to the double bond will increase the stability of the alkane. With hyperconjugation, we can explain the stability of carbonium ion. The order of the stability of carbonium ion is tertiary carbonium ion is more stable than secondary carbonium ion, which is more stable than that of primary carbonium ion. In general, greater the number of hydrogen atom attached to alpha carbon atom, the more hyperconjugative forms can be written, and thus greater will be the stability of carbonium ion. In the case of tertiary carbonium ion, there are 9 equivalent forms are possible, but in the case of secondary carbonium ion, there are only 6 hyperconjugative resonance structures. But in the case of primary carbonium ion, there are 3 hyperconjugative resonance structures. So the tertiary carbonium ion is more stable than that of secondary and primary. Similarly, we can explain the stability of free radicals. That is, the tertiary free radical is more stable than that of secondary free radical, which is more than that of primary free radical and than that of methyl free radical. The next electron displacement effect is steric effect. It refers to the influence of the spatial configuration of molecules upon their stability and properties as well as upon their rates of reaction. Steric hindrance at a given atom in a molecule is the congestion caused by the physical presence of the surrounding ligands, which may slow down or prevent reactions at the atom. Here, formaldehyde and acetaldehyde. In the case of formaldehyde, the carbonyl carbon is bonded to 2 hydrogen atom, but in the case of acetaldehyde, it is bonded to hydrogen atom and a methyl group. Since the methyl group is larger than the hydrogen atom, the steric hindrance is greater at the carbonyl carbon in acetaldehyde than that in formaldehyde. A substitution reaction on a halide by a hydroxide does not work in this case because of steric hindrance. The second figure represents the same reaction with the spheres replacing the alkyl groups to show the spatial perspective. In the case of butane, the stability order is trans-2-butane is more stable than cis-2-butane, which is more stable than that of propane, which is more stable than that of ethane. Here, in disubstituted alkanes, trans isomers are more stable than cis isomers due to less steric hindrance. Because in trans, bulky groups are in opposite sides, so less repulsion between them, as there is more repulsion in case of cis due to same side of bulky groups. Also, internal alkenes are more stable than terminal ones. Another example for steric effect is butane conformations. Among the various conformations of butane, the anti-staggered conformation in which 2 methyl groups are the farthest from each other is the most stable, and the fully eclipsed conformation in which 2 methyl groups are the nearest to each other is the least stable. This is because the steric repulsion between the bulky methyl groups is the least in the anti-staggered conformation, while it is the most in the fully eclipsed conformation. That is, highest energy as methyl groups eclipsed. And also steric hindrance in the totally eclipsed form. Here the dihedral angle is 0 degree. This is the anti-staggered conformation. Here lowest energy has methyl groups and the dihedral angle between 2 methyl groups is 180 degree. In amines, there is a lone pair of electrons on nitrogen. The tendency of nitrogen to share these electrons with acids is responsible for the basic character of amine. Aliphatic amines with Kb between 10⁻³ and 10⁻⁴ are stronger bases than ammonia. Like ammonia, amines are the strong bases and react with the mineral acids to form ammonium salts, from which they can be liberated by the treatment with a strong base like sodium hydroxide. That alkyl amines are stronger bases than ammonia can be expressed in terms of its inductive effect of alkyl groups. Alkyl groups, by their electron releasing effect, concentrate electron density on nitrogen and hence make the lone pair of nitrogen more easily available for sharing with acids. Also, the electron releasing effect of alkyl groups stabilizes the alkyl ammonium ion formed and hence shifts the equilibrium in forward direction, making the alkyl amines stronger bases than ammonia. Thus, the basic character of aliphatic amines should increase with the increase of alkyl substitution. In the gas phase, the basic strength in nature is as expected, that is, tertiary amine is more basic than secondary amine, which is more basic than primary amine, which is more basic than ammonia. However, the order of basicity in aqueous solution does not follow the expected trend. Overall basic strength varies as secondary amine is more basic than that of primary amine, which is more basic than that of tertiary amine. The steric effect refers to the crowding of alkyl groups around nitrogen atom, which hinders the attack of proton on the tertiary amine molecule, and this decreases its basic strength. We can explain the acidity of carboxylic acid by steric effect. The acidity of carboxylic acid is decreased by the presence of bulky groups in its molecule as they cause steric hindrance to the stabilization of the carboxylate anion through solvation. In the case of carboxylic acid, the pKa value is 5.05. But in the case of 2,6-di-tertiary butyl benzoic acid, the pKa value is 6.25. That is, as a result of the steric effect induced by the two bulky tertiary butyl groups at the two ortho positions of the carboxyl group is found to be less acidic than benzoic acid. Another example of steric hindrance is shown in the esterification reaction. That is the mechanical hindrance offered to the approach of a reagent to the reaction site on the substrate by bulky groups present in the vicinity on the rate of reaction. The acetic acid is esterified easily when refluxed with an alcohol and concentrated sulfuric acid. With increase in the number of alkyl groups on the alpha carbon of the acid, the rate of esterification decreases due to an increase in the steric hindrance offered to the approach of the alcohol to the reaction site with increase in the size of the alkyl group. So, the rate of esterification decreases in the order acetic acid is greater than that of propanoic acid, which is greater than that of 2-methyl propionic acid, which is greater than that of 2,2-dimethyl propanoic acid. Benzoic acid is esterified easily when it is refluxed with methanol in presence of HCl. But in the case of 2,4,6-trimethyl benzoic acid, it is not esterified even when it is refluxed with the methanol for a very long time. This is because the two methyl groups sterically hinder the approach of the alcohol molecule to the reaction site on the acid. Today we have discussed about the mesomeric effect, hyperconjugation and the steric effect. And also several phenomena in organic chemistry can be explained on the basis of existence of mesomeric effect, hyperconjugation and steric effect. Thank you.